And we're live. Welcome, everyone. Mr. Stoker will be your host today. All right, the whole semester in, 20 minutes? Is that what we're saying? 20 to 25? No guarantees. Okay, we started the year with uncertainty. Remember we did the meter stick drop and learned about how to calculate uncertainty and whatnot? Not going to be on the final, so don't worry about it. Okay, we then started motion, which is chapter 2, motion in one dimension. Although we actually started using a packet, not from the book, because the packet taught us ways to represent motion visually, like motion maps. Those are fairly handy ways to keep track of the motion of something, because the spacing tells you the distance and the snapshots were in equal intervals of time, and this would then be speeding up, maybe going constant for 1 second, I don't know, and then slowing back down again. You could even show stopping by dropping down, and then you could reverse directions if you wanted. That was the idea of motion maps. We also could use a position time graph to track motion. And we could also use a velocity time graph to track motion. So we had motion maps, we had those two types of graphs, and you could also describe it in words. So sort of 4 different ways for that. We quickly realized that when you're doing a motion map, that it can tell you whether you're going forward or backward. If you're moving away, that's, a positive slope is one direction, a negative slope is another. In fact, we defined the slope to be velocity, how steep the line is. And because the slope can be positive or negative, velocity then could be a positive or negative, meaning that it has a direction to it. Positive was one way, negative was the other. So we got our first introduction to what a vector is without really knowing the word vector yet. We dealt with vectors. A lot of people say velocity is speed plus direction. Partly true. Remember, this is your displacement, your change in position, which is not always the same as the distance that you travel. If you go in a circle, your displacement's 0. If you come back on yourself a little bit, it's going to be less than your total distance. So that also made velocity different. We then said we can take these same things and create a velocity time graph. So this is a positive steep here, which would be something like this. Slope is 0, so the velocity drops down. And the velocity becomes a larger negative at the end because it's steeper there. If I had a velocity graph that was, say, doing something like that, then I could define acceleration as the change in velocity over the change in time. It could be positive or negative as well, so it was also a vector. So we came up with our first 2 equations and definitions, velocity and acceleration. How velocity, or I should say how acceleration shows up on a velocity time graph, though, would be some kind of change in steepness, which would be like a curve or a spike or something where it changes its steepness. How acceleration shows up on your motion maps is a changing rate of the spacing, basically. We had a difference between average velocity and instant velocity. Remember, instant velocity was what was the slope of the tangent line at that exact point, whereas the average velocity was take the 2 points and connect them, and whatever the slope of that is, that was the average velocity. This was the instant velocity. Didn't come up a lot, but a little bit. From our graphs of like these guys, we came up with 3 shortcut equations that were the kinematic equations. I know you have them up on the board, or maybe you've memorized them by now, I don't know. But it's probably worth reviewing what they are, because they come up from time to time, right? Whoops, did that wrong. And then the 4th one we know is when you do not know the time, we would use that one. These only applied when you had a constant acceleration and a straight line motion, which sometimes they will call uniform acceleration in some problems. That's what they mean, though. Constant acceleration and linear motion. So we had problems that dealt with that. And remember, the reason why it had to be those two is because we got these shortcuts from graphs like this, where you were moving in a straight line with a constant acceleration. So the shortcuts are only valid for the situations like that. So that was chapter 2. We then moved on and did chapter 3 in our book, which was motion as well, but now we went in 2 dimensions. So moving in the x and y direction at once. This is where we hit vectors head on, where a vector is a quantity with magnitude and direction. Oh yeah. Whereas scalar was something that only had a magnitude. So things like velocity or acceleration or force or momentum all were vectors, whereas things like time, energy, mass were not. How did we add vectors together? Remember, the simple case was if we had 2 vectors, we could slide them head to tail, vector A and vector B. We could create a right triangle, and then the resultant here would simply be found by doing Pythagorean theorem. And the angle up here could be found by doing the inverse tangent of the opposite side to the adjacent, in this case B over A. Usually, though, it wasn't that straightforward. Usually you would have something at least one vector at an angle. And so when that was the case, we would take that vector and split it up. Let me get rid of that guy. Put it there. X in the y, or A in the y and A in the x. And I could use sine and cosine to do that. If you're not comfortable with that, that's not going to be in this video, but come in and see me and we'll go over that before the final. We still would slide these head to tail. So B was there, A was there. And then we would be thinking to ourselves, though, that this partly goes over, partly goes up, and the result looks like that. In other words, I have forced it to be a right triangle by splitting it up and adding components. This is the A and the x, this is the A and the y. I add these two together, and that's one side of the triangle, and I already have this one, and then I can find what the resultant is the same way as we did up here, and I can find what the angle is. We had some problems like river problems were kind of the classic. You know, you have this river flowing with a certain velocity this way, and you're trying to cross the river with you going, you know, the velocity of the boat a certain way. And maybe the question was, how quick is the boat moving compared to someone on the shore, on the bank? And what angle is it actually moving at? Or some version of that. Maybe you had to find how far the boat hit downstream if it went straight across, or if the boat went at an angle, you know, where would it end up hitting, or any of this kind of stuff, or what angle would it need to hit to go straight across. They're all vector problems like this. We then started dealing with the real meat of Chapter 3, which was projectile motion, which is defined as something moving with a constant velocity sideways, horizontally, but accelerated motion vertically. So kind of the classic problem for projectiles is if you fire a cannon or whatever else you want to fire horizontally off a cliff, how far is it going to go and how fast is it going to be going when it gets there? So we took that problem and said the big idea is if you just drop the cannon straight down, the time is going to be exactly the same as the time to go through the air sideways, because the vertical and the horizontal components are independent in projectile problems, so we can treat them separately, which is nice because we can't use the kinematic equations for something that's moving in a non-straight line. So we have to treat it as if it's moving sideways at a constant velocity. So imagine something like this. And then downward, it is accelerating. So it is speeding up. And where it's actually moving is the combination, which doesn't match my chart at all, but you get the idea. That produces the parabola curve there. So then we would use kinematic equations to say, well, how long does it take for this thing to fall? And we usually knew that the initial velocity was 0, and we're solving for the time. The acceleration we would know is about 10. We typically would call positive up, negative down, so that's a negative 10. We usually would know the height of the cliff, delta y. Say it's 50 or whatever. Negative because it's going in a negative direction. And remember, we take the kinematic equations and replace the x's with y's when they were vertical and the subscripts with y's and keep everything horizontal in the x to just keep track of it. When you would crank this out, remember, it ended up we'd use number 3 quite often. And when you'd use number 3 but tweak it for the y direction, this was 0. It would then simplify and you could find the time fairly easily. Once you knew the time then, you could say the change in position is the velocity in the x multiplied by how long it takes to fall. Just going to move at a constant speed until it hits. Now, that was the easier version. The tougher version, then, is when something is fired upward. But really, the only thing we do different is we take that initial velocity and we break it into its v initial in the x and v initial in the y. And then we say the time it takes to go straight up to the same height and straight down using this initial in the y is going to be the same time this thing takes to do what it actually does and eventually come down and hit the ground. So I'm still starting in the same place. What made it trickier though now is when you'd plug this in, it did not simplify to something easy because now this isn't 0. So it ended up being quadratic. And you usually had to use quadratic formula and come up with 2 roots. One of them was usually a negative something, so we didn't care about that. We go with a positive root. Negative root would mean you're going back in time somehow, which just doesn't fit for what we're usually doing. And then once you know the time, you could say, well, the sideways position is still the initial velocity in the sideways direction times the time. It would be how far it goes. Or maybe they ask you to find how high it is at the peak, which you can use the vertical part of the problem to figure that out, knowing that Vy will be 0 at the very top. Or maybe it was what's the velocity at the very end, which you knew it would be the same velocity sideways, and then the V vertical is the same as the vertical velocity is in this case. Put them back together with Pythagorean theorem, find the angle, and you've got the answer for that one. Okay, that was basically chapter 3. Chapter 4, we then moved on and did Newton's laws. And for that, we started off by saying we really have to be able to figure out something about forces. So we drew force diagrams, which are sometimes called free body diagrams because you're imagining the object is free off by itself in space and you can just draw the forces on it. Maybe not space, but off by itself. And you can pretend like all the forces act from the center of it. So even if it's a cart or a car or whatever, pretend like they act from the center of mass. So we'd have things like the weight straight down. We'd have the normal force, which is the surface pushing back up. Maybe there was a pushing force of some sort this way. And maybe there was friction, which I usually use lowercase f to write that. This would help us figure out what is the leftover force. Or in other words, what is the net force? Why we cared about that is because the acceleration depended on the net force. In fact, the acceleration is caused by the net force. The bigger the net force, the bigger the acceleration. But then we also learned along the way that mass plays into it equally well. So acceleration is the net force, or sometimes we could write the sum of the forces, divided by the inertia, which is measured by the mass in kilograms. It's that ratio. Although a lot of times we would write it in a more convenient form like this, or write net force or whatever. So a lot of solving these kind of problems have to do with, can you find what the net force is, and hopefully you can draw a good force diagram to help you figure that out. As an example, let's look at the elevator kind of problems, which are sort of the classic vertical problem. So let's say there's a tension in the elevator, the cable, and then there's the weight of the elevator. And in this case, there are no sideways forces. So what I know here is if tension is bigger than the weight, then this is going to accelerate upward. So I would have a net force upward if tension is bigger than weight. If weight is bigger than tension, then that would mean I have a net force downward, so it's accelerating in the downward direction. That doesn't necessarily mean it's moving downward. We'll get back to that in a minute. If the forces are balanced, so the tension does equal the weight, then the acceleration is zero. There is no change. Which means then either I'm not moving, which is what everyone thinks of, or moving at a constant velocity. Now, think about the situations. If there's a net force upward and you're moving upward or not moving, then you're going to start accelerating in the upward direction. If you get to the top of the building, though, and you start to slow down, now you have the net force downward situation. You've got to slow down, so there has to be a net force in the opposite direction to slow you down. So then the tension becomes smaller at the top. If you're moving downward and you're accelerating downward, then the net force is downward. If you're moving downward but you're accelerating upward, meaning you're slowing down and you get to the bottom floor, then the tension up has to be bigger to slow you down. So quite a few situations you could do there. Another one that we had was something like on a hill, something sliding down. So we then would draw the weight down, split that up into part of the weight is holding it into the hill, and part of it's holding it or trying to slide it down the hill, weight in the x direction. Usually we tilt the xy axis to match the slope. Normal force is upward, which I know that balances the weight. I'd have some friction backward, and the acceleration was usually produced by the weight in the x being bigger than the friction, and then we could figure it out from there. Now remember, we learned about friction at this point too, that friction depends on two things. The coefficient of friction, which is a measure of the roughness of the surfaces, and the normal force, which is a measure of how much they're smashed together, or I like to call it the smashed togetherness. This is a number somewhere between 0 and 1, with 0 being no friction, 1 being maximum. Smashed togetherness is measured, of course, with the normal force, and that's just going to be measured in newtons. So then in this problem, we could figure out friction just by using this and using that. Normal force would have to be equal to the weight in the y. We'd use sine and cosine. This angle up here is the same as that angle down there, which is usually a tricky part for people. Really the only other main thing, well, we had weight versus mass. Remember, mass is a measure of your inertia in kilograms. Weight is a force. It's how much gravity is pulling you down, which is 10. On the Earth, gravity pulls with 10 newtons for every 1 kilogram. So that links those two ideas together. We had Atwood's machine, which was sort of like the finale of this stuff, which is one block is pulled up a hill while another one is falling and doing the pulling. Remember, the trick, or at least the easiest way to solve those, is pretend they're one system. And those are just one big blob with friction acting against it, and this weight is what's trying to pull it down. And so then you could solve for the acceleration, and then once you've got that, to try to find the tension inside, you then had to separate these two and just consider the system to be one of them. And now the tension down would be bigger, weight down would be bigger than the tension up. You know the acceleration of 1 is the same as the acceleration was over here, which then would allow you to find the tension. That's chapter 4. We move to chapter 5. The nice thing about chapter 5, it was in a lot of ways just an extension of chapter 4, which is circular motion. Oh, one thing I forgot for chapter 4, Newton's 3 laws. We know his first law is inertia. An object in motion stays in motion. One at rest stays at rest. His second one we've already said. His third law is forces always occur in pairs, or for every action there's an equal and opposite reaction. The circular motion stuff is for things to move in a circle, they need an inward force. They just don't move in circles. And that inward force is governed by how much mass the object has, its velocity, which is really just its speed since it's always changing directions, and the radius of the turn that it's making. Sharper radius would be, or smaller radius would be like a sharper turn. So we started doing cars going around roundabouts, and we did yo-yos whirled on strings and those sorts of things to figure out how much inward force is required. And that inward force could be provided by tension, like a rope. It could be provided by a surface, a normal force. It could have been provided by friction. And then we also introduced the idea that it could be provided by gravity as well. So we did some planets and satellite problems and things like that. This could also be called centripetal acceleration, which they'll sometimes write. And then this just simplifies to Newton's second law. Remember, centrifugal force is the feeling of being pulled outward. It's not a real force in the sense that it doesn't have a force pair to it, but it's a very useful thing, and you can treat it as a real force in a lot of situations to solve problems. But it's just caused by the feeling of inertia. The last thing in this chapter was Newton's law of universal gravitation, and Newton said that for whatever reason, all things with mass in the universe attract each other. And how much they attract each other depends on how big mass 1 is, how big mass 2 is, and the distance between them. With the distance between them being more important, and it's squared on the bottom. This was a conversion constant, gravitational constant, 6.67 times 10 to the negative 11th. Really, really small number, telling us that gravity is the weakest of all the forces because it's such a small conversion. This was also the first inverse square law, and actually the only one so far that we met up with, meaning that the force is inversely proportional to the square of the distance. So if you double the distance, you've cut the force in 1/4, or by 1/4. If you triple it, it's 1/9 weaker. Quadruple it, it's 1/16 weaker. So inversely proportional to the square of the distance. Okay, that was chapter 5. Chapters 6 and 7 I'll go quicker because we just went through the test over those. Chapter 6 was energy, which you could say is the ability to cause pain or produce change. We measured in joules, and we know that roughly, well, not roughly, 4,186 joules is 1 food calorie, if you need to know that. We had kinetic energy, which is energy of motion, 1/2 mass times its velocity squared. We had potential due to gravity, mass times gravity times height. We had potential elastic, which is stored in a springy type thing. X is the stretch or compression. K is the spring constant, how stiff the spring is, in other words. We also had this category dissipated energy, which is energy transferred to heat or sound, as heat or sound, which there is no formula for that. We used pie charts as a tool to try to help us think about where the energy is being stored at any one time. You don't have to do them, but I think they're pretty handy ways to keep track of it and set up the problem. Before and after pictures. Big idea is that energy is always conserved. How often is it conserved? Always, right? That's why the word always is in there. Now, not mechanical energy. Mechanical energy is these three together, not always conserved. Only conserved if there's no dissipated energy by forces. Remember, forces that dissipate energy are called non-conservative forces. We also had work. Work is force times distance. And work also is equal to the transfer of energy. We had power, which is how quickly you do work. Work divided by time, which is measured in watts. Chapter 7, momentum. We had the big idea that momentum before equals momentum after. Some fine print here as long as there's no net external force. Momentum is the idea of oomph, or inertia in motion. It's mass times velocity. It doesn't have its own unit. It's just kilograms times meters per second. For that, big idea then with the setup would be, if it's an elastic collision, the momentum before equals the momentum after. It should be an equal sign. Elastic collisions meant that kinetic energy was conserved, and they bounce apart. So think to yourself, magnet ends of the carts. When this was true, it also meant we could say V1 minus V2 equals V2 prime minus V1 prime. I didn't do all the 1s and 2s up here. Okay, now it's complete. We also had an inelastic collision. An inelastic collision meant that really kinetic energy is not conserved. That's the definition. So there's some kind of dissipated energy happening. The extreme case of this is called perfectly or completely or totally or whatever adverb you want to throw in there to modify inelastic. If it's perfectly inelastic, then they stick together and move as one, which is typically the kind of problem we would solve. Right? This guy plus this guy, and then they stick together. We can also use momentum for explosions. So it's really good for explosions, which are just things pushing apart, and collisions. If that's involved, you want to use momentum almost always. The last piece here is momentum can change whenever there's an impulse. And that impulse is equal to force times time, and it also changes the momentum of the object. And that is that.